Good morning to everybody. For those who entered the room and didn't notice that there is a coffee served on the back, please help yourself. There is still time to do that. When I may get to the main part of the presentation, I will not let you go there anymore. So this is the second part of our innovation session from DuPont. Yesterday that we talked about the new innovative fluid for the liquid immersed transformers. Today we continue the topic on liquid immersed transformer, talking about the innovation in the area of insulating papers. There were already a couple of presentations during this seminar, during the last 2 days, about the innovation in papers. There was something about high temperature papers. There was innovation about the thermally upgraded kraft papers. So now I would like to talk about the innovation which we at DuPont introduced for that range of products. So quickly I will introduce the DuPont company and the profile which we are. I will remind you what is Nomex paper, which you probably know if you are in the business. And then the main focus on the new innovation, which is the new Nomex paper type 910. As a DuPont, we are the global company focusing on the science-based development in different areas. There is a variety of various areas of various businesses which we cover, and we want to put lots of science behind that, not just provide the useful products for the industry. We want to put lots of science, and we have a great background, great experience in different areas of the chemical industry. Excuse me. Yeah, the three major areas of our focus is the agriculture and nutrition, the bio-based industrial materials, and the advanced materials. Yesterday, when Giorgio talked about new insulating fluid for the transformers, the vegetable fluid, that was definitely in the area of bio-based materials, the agriculture and nutrition business joining or supporting the electrical industry. Today, I'm more in the area of advanced materials, talking about synthetic material which is used and could be used in the power transformers. For a number of years, DuPont supplies many various insulating materials for the electrical industry. Nomex paper and board is one of them, while there are other ones like Kapton polyimide films, the Mylar polyester films, Teflon. Those names are so well known, not always people associate them with DuPont because these are the common brands commonly used, including the performance polymers used in motors or transformers. So there is a variety of products from different areas of the chemical industry which serve the electrical insulation purpose. And definitely I am representing group of Nomex. So Nomex is meta-aramid material used for electrical insulation for 50 years already. So well-established product, proven in many demanding applications. This is a meta-aramid material, so it combines the aromatic component, the polyamide, providing very strong bonding between the molecules, which translates into very high temperature resistance. So Nomex, which we know for the electrical insulation in different forms, is used for the firefighters, for the protective apparel, for the hot gases filtration, and different applications requiring high temperature performance. When talking about electrical applications, liquid immersed transformers business uses paper and board. So the point was at the development of the Nomex paper and board to have it in the form of paper and board to facilitate manufacturing of the liquid immersed transformers. So when we make the polymer, we combine it into flock and fibrate to make the structure similar to the paper, and then we actually use the paper making machines for making the paper for the electrical applications. So although it does not have any cellulose inside normally, it is made on the paper making machine. So that's why sometimes when I hear that people say they could use either paper or Nomex, this is not fully correct, because Nomex is also a paper. It's just different chemical composition, but it is a paper in a sense of manufacturing process. And except of paper, we can also make a board. Board is also available for the applications in the transformers. What is important to understand for the users of the material, for the designers of the transformer, is that the paper and board may have a different structure. It is critical for the right impregnation of the material. With the oil, it is critical for drying. So users should be aware that if there is a high-density material, like the one on the right-hand side of this slide here, it's more difficult to impregnate it with oil. It's more difficult to dry it. It requires some more time, maybe some higher temperature, maybe some better viscosity of the oil to impregnate it properly. If we have the low density material, like on the left-hand side, it's definitely easier to do that, easier to process that material. But on the other hand, the material is softer mechanically, does not have as good dielectric strength. So there is always a balance between the properties of those materials. As I said, there could be a paper, there could be a board, various densities, so plenty of various components could be made. Basically, all the components which are needed in the transformer construction could be made of Nomex paper and board. So this is the solution which is known, this is the solution which is used, and used in the very demanding applications. So now moving to the development. No coffee anymore. What you get, you have. We realized that there is a gap between the conventional material, which is a cellulose material, most common material in the construction of liquid immersed transformers, and the high performance, also high cost, high temperature Nomex material. We realized there is this relatively big gap between the materials, and this could be expressed by showing the life curves of the insulation or the temperature withstand characteristics of the material. We see that those different materials, what we show here, the conventional cellulose or the thermally upgraded cellulose, they are materials in the range of 105 degrees class or 120 degrees class for the temperature withstand. While Aramid Nomex is around 200 degrees. Measured in the air, it's 220 degrees. The testing, the most reliable testing, which is available for testing in oil, it shows the temperature class better than 180 degrees. So there is this big span of the properties of the material, of the currently available materials suitable for the liquid immersed transformers. So our aim was to fill this gap, of performance of the materials and to provide the industry the solution which could be intermediate solution. Like we know that cellulose, of course, is the most common material, the cheapest material, and performing excellent in number of transformers operating for tens of years. We know that Nomex Aramid could be used for the specialized applications, which normally allow for squeezing the design, for reducing the size and weight, for numerous applications like the wind turbine transformers, like the traction transformers in locomotives, a number of power transformer applications like the repair business of the transformers, also mobile transformers which have to be transferred quickly, filled with oil, fully assembled. These are the applications for the high temperature Nomex. Now, we know that industry having sophisticated design tools, they are equipped to optimize the design, to make little changes in the design, to optimize the design in terms of the performance. We see the new requirements for the efficiency. The next session will address the efficiency aspects in the transformers. So we believe there is a possibility of providing more materials to fill the gap between the class A materials and class 200 degrees materials, to provide more solutions, more tools for the designers to design the equipment to fit the specific specification requirements. So this could be efficiency, this could be the losses, this could be the size or the lifetime overloadability of the transformers, number of different aspects possible to address. So what's the solution which we propose? It is basically based on the fact that when cellulose material is aging, it loses its mechanical integrity. Those who deal with the large power transformers and do the post-mortem analysis, they know that the aged material, the old material, can still withstand the dielectric stress, still maintains the dielectric strength, while mechanical strength is disappearing. Mechanical strength, which could be expressed by the degree of polymerization, the parameter which shows the length of the cellulose chains, and normally assumed level of 200 for the degree of polymerization means that the material is considered dead. It's not useful anymore. It means that the mechanical strength of the material is less than 40% of the original mechanical strength. So this is what is considered the end of life of the insulating material. Keeping that in mind, this means that the material exposed or the transformer exposed to some vibration, to some mechanical shock, could lose the integrity, the material could crack, and then this could lead to the electrical failure as a consequence. So that mechanical strength or losing mechanical strength of the paper, degraded paper, was our focus for developing the new solution. And here is the new solution. This is a cellulose paper improved with the Aramid binder on the surface. Cellulose as the relatively cheap component, very common, with good properties, with only deficiency that when it ages, it loses its mechanical performance. So we want to help cellulose to survive the thermal stresses longer during its operation and extend its life by adding the Aramid binder. So this is the same Aramid binder, or Aramid component, which is used in the regular Nomex papers, which I mentioned before, which I talked about before. So that's why the name of the product is still Nomex, although it's different class of Nomex. This is a medium performance Nomex, only 130 degrees class material, but allowing to operate at temperature higher than cellulose. So it's not improving the cellulose by chemical modification, by adding nitrogen like it's done in the thermally upgraded paper. This is by adding the Aramid component. So when material operates in a transformer and is exposed to the thermal stress, the cellulose can degrade. The cellulose will likely degrade as the regular cellulose in the regular cellulose paper and board. The point is that the Aramid component to degrade would require the temperature of more than 180 degrees, more than 200 degrees, which is not a usual temperature for the cellulose-based transformers. So by this, the Aramid component will survive much longer and will still maintain the mechanical integrity of the material used as an insulation. So this could be represented as a shift of the lifetime characteristics. So for the given temperatures, the expected life of the insulation will be longer because the part of the insulation will degrade while the other part will stay untouched. When we look at these characteristics, we could look at them also differently in the horizontal direction. We could say that for the given reference lifetime, in this case, this is 65,000 hours marked, which is like 7.5 years. Each material has got certain thermal class. We say that the conventional cellulose could operate at the temperature about 95 degrees. To be more precise, the IEC recognized the normal temperature as 98 degrees. The thermally upgraded kraft paper could operate at 110 degrees. Our material could operate at higher temperature because of that improvement from the Aramid component. So we could say that the lifetime characteristic is either shifted up to extend the life or shifted to the left on this life characteristic to extend the to increase the operating temperature of the material. This is the result of the short time aging of the material. That was a quick aging, only 2 weeks at the temperature of 170 degrees. So that was to observe quickly. That was like a scouting test. And actually, anybody can do it. Anybody who has got some minimal capability for testing the materials, this could be done relatively easy. That was 2 weeks testing at 170 degrees. Material was impregnated with mineral oil. We can see 4 different materials here. We can see the regular kraft cellulose, the thermally upgraded kraft, then our new solution, Nomex 910, and more traditional Aramid paper, Nomex 410, the most common grade used in the electrical industry. So what we see here, after these 2 weeks of aging at 170 degrees, we could see significant drop of mechanical properties of the kraft paper, also thermally upgraded paper. When looking at Aramid, the 100% Aramid paper, there was nothing happening because that was only 170 degrees. The material could operate continuously for years at the temperatures above 180 degrees. So testing for 2 weeks at 170, that did not change any properties of the material. And you can also see the new solution, the Nomex 910, which is in between. I said before that this is supposed to be an intermediate solution, and this short time test showed that it is an intermediate solution. It is an intermediate solution between the cellulose papers, whether kraft paper or thermally upgraded kraft, and the Aramid solution, the 100% Aramid solution. So we managed to achieve this goal by having the material in the intermediate characteristic. Obviously, for the commercial use, for the long-term performance guarantee, we performed long-term study, and that was a long-term advanced study in the sealed tube testing in the lab. So that was like more than 100 tubes tested at different configurations, combining the mineral oil, combining the presence of copper, coarse steel, different components which are normally part of the transformer construction, and that was done according to the recent IEEE standard. Recent IEEE standard, the number is on the bottom, the C57-100, which was published in 2011. So that procedure was followed, and this required testing number of temperature points. This required of testing the points with the specific span in the temperature. So that was number of points with intervals of 15 degrees Celsius to generate the proper lifetime characteristic of the material. So what is also important when testing the material, we call it testing candidate material, we also need to use the reference material. So the reference material was the thermally upgraded kraft paper, which is assumed to be the thermal class 120, which means that it could operate at the temperature of 110 degrees for 180,000 hours. So this is the definition of the thermally upgraded kraft paper. It has to be able to withstand 180,000 hours, operating at the temperature 110 degrees, providing the specific mechanical performance or the insulating performance. So that was the benchmark, that was the comparative material. When we used exactly the same method for testing thermally upgraded kraft and our new product, we got to the level that to get to the same condition of the material, to the same aging condition of the material, we maintained to have this 180,000 hours with the temperature 120, meaning that the thermal class is 10 degrees better. So that was this methodology based on the comparison of 2 different materials, one which is proven, well-known system. In this case, it was thermally upgraded kraft paper in mineral oil. Our new system was our new paper, improved with the Aramid, again in mineral oil, tested with exactly the same methodology. So this long-term testing, which took months of aging studies, of course not at the temperature of 120 degrees. At 120, we would need to wait 20 years for the results. We do the accelerated testing, which takes months of testing at different temperatures and precise measurements of the mechanical strength of the paper after that. So this have proven that this material is indeed at least 10 degrees better than the thermally upgraded kraft paper. Obviously, we measured a number of different electrical, mechanical characteristics to provide the full characterization of the material. This is just an example of the dielectric tests. Honestly speaking, it's a bit surprising to me. I would not expect that adding some aramid component to the cellulose would improve the dielectric performance as much. So we can see here the test results for the one layer of 3 mil paper, 3 mil meaning 80 micron, and 80 micron in millimeters. So one layer or 4 layers or 7 layers of paper, actually they perform better than the comparative thermally upgraded paper. So this could be another opportunity of optimizing the designs if we include in the design the better dielectric strength of the paper. That could bring another benefits to the design. Of course, we did the full characterization. This is available in the data sheets. Please use the website Nomex 910 or Nomex paper, DuPont.com. The data sheets are available there for more information on the mechanical, electrical properties, but also on the aging study, on the aging evaluation or the thermal evaluation of the material which was performed. Excuse me. What is important from the user perspective? There are two major ways of application of the material. One would be to extend the life of the insulation system, meaning the design stays unchanged. I mean, stays unchanged, meaning the conventional design with mineral oil and cellulose paper is used. So no need to redesign the transformer, basically the same design as it could be normally with the cellulose paper. If we put the material of improved performance, thermal performance, the life of this transformer would be extended, assuming that the insulation life is the key factor. So the insulation life and consequently possibly life of the transformer could be extended. This could be also translated to the fact that overloading capability of such transformer could be higher because the insulation would be less sensitive to the higher temperature, short-term or long-term higher temperatures during the overloading periods of the transformer. So in this sense, the material of improved thermal class could be a tool for improving the overloadability of the transformer. The other option of the design is using this additional 20 degrees given by upgraded performance, using it for the design, rating the transformer for 20 degrees higher temperature. So instead of using normal IEC temperatures of 65 degrees rise for average windings or 78 degrees for the hotspot, the higher temperatures could be used to optimize the design. So maybe some cooling ducts could be removed. Maybe some cooling from the outside of the tank could be removed to make the design more optimal. Oops, excuse me. This is the example of the tables from the IEC and European standard for the transformers using high temperature materials. We talk about material which is 130 degrees. In the IEC terminology, this is already high temperature material because it's higher than the cellulose material, which is 105 degrees. So we can see the guidance in the available standard that different temperature rises could be used for the windings, insulated with materials of whatever, 120 or 130 degrees class. So this could be used as a guidance. Of course, there is an aspect of convincing the customer, convincing the user of the transformer that temperatures different than conventional IEC limits are acceptable. So it's not 65 degrees rise for the windings anymore, but 75, for example. So, or the hotspot is not 78 degrees anymore, but it could be 90 or 100 degrees because insulation allows for that. So definitely there is a standard reference for that. Of course, different limits could apply if the alternative fluids like esters or silicons were used. So this guidance is applicable. The reference in the standard world is existing. So there is a tool for the designers to use these higher numbers for the design. To summarize, yeah, I said before that the development was based on the fact that we identified the gap in the existing materials, in the available materials. Between the cellulose and the high-temperature Nomex, there was a space for different materials, and this is the example of the material. The important thing is that we did not actually develop a new chemical, new component for making this paper. We still used the cellulose, which was known and used. We used the Aramid material, which is well known since 50 years. We just combined those two materials. So the innovation here is the right combination of the material to fit the purpose of meeting the medium performance of the material. And the last point, which is also critical, people or the industry knows the Nomex material as a high-temperature material. Since now, Nomex is not only that high-temperature material of 220 degrees class. Nomex 910 is a medium performance material of only 130 degrees class. So since now, when using the name Nomex, the users and manufacturers have to be aware what kind of Nomex they talk about. Nomex meaning has changed a bit by extending this material range which we have now in our portfolio. Material is now available commercially in 3 thicknesses only: the 80 micron, 130 micron, and 180. This is the current range of the materials available, typically serving the layer insulation in the distribution transformers. The 80 micron could be also used as a conductor insulation for the power transformers. We are in the stage of development of thicker materials. So I believe before the end of this year, we will have a good progress in the development of paper up to 0.5 millimeter thickness. So 0.5 millimeter thickness should be also available, maybe not commercially, but we believe that the product will be finalized before the end of the year. So this is the target. The testing was done. It could be diamond dotted for making the paper for distribution transformers. It could be available in the form of crepe paper. Of course, it could be slitted for the conductor wrapping. So this type of materials coming or popular in the normal either cellulose or the Nomex, they would be available in the form of Nomex 910, and the transformers are also built with this material. You're welcome to visit our booth upstairs, the B19 at the upper floor here. We have an example of the transformer built for China grid. There is a couple of hundreds of these transformers already operating in the Chinese grid. The aim was to improve the overloadability of those transformers. So you are welcome to see the transformer and see the Nomex 910 used in the real example of the construction.